Alright, problem number 20 in group theory. Let Sn denote the symmetric group on n letters and An denote the alternating subgroup. Show that an element of Sn of odd order is always in An for part A. Okay, this is a fun problem. So we're going to pick an element in Sn, let sigma be in Sn with odd order. We want to show that sigma is in the alternating group, meaning that it is an even permutation. Every element of Sn can be expressed as the product of disjoint cycles, and the order of a product of disjoint cycles is the least common multiple of the cycles. Let sigma equal, we'll say gamma 1, gamma 2, c dots, gamma n, and let me put this in the center. Okay, so two facts here. We can write sigma as a product of disjoint cycles, so where each gamma I are disjoint cycles, and we know that the order of a product of disjoint cycles is the least common multiple of them. So if one of them was even, then the least common multiple would be even, meaning this guy would be even. Hence, each gamma I is also odd from this second sentence. And for each gamma I are disjoint cycles that are odd, and when I say odd, I mean odd in length. They're odd in length because we're talking about length. Is the least common multiple of the lengths of these cycles. Least common multiple of the lengths of the cycles. Okay. Of odd length. Okay. And you could use the fact that odd length cycles are even cycles, or you could just quickly prove it. It's not too bad. Consider c dots k. Okay. If we consider just a k-length cycle, well, we can write this as something like this. Some dots. And if k is odd, then the cycle, well, yeah, if k is odd, then the cycle can be written as the product of k minus 1 transpositions, which would be an even number of transpositions. Essentially, we're saying that since each gamma is odd, we can take that odd cycle and we can write it as an even number of transpositions. Hence, we're taking an even number of transpositions and multiplying them with an even number of transpositions, an even number of, and so we're just adding up essentially a bunch of even numbers. Thus, sigma is the product of an even number of transpositions. Therefore, that's the definition of being in the alternating subgroup. Okay, so that finishes part A. An element of Sn of odd order is always in An. Part B, we want to show that, conclude that Sn has more elements of even order than of odd order if n is greater than or equal to 4. Okay, so we're just going to define some terms. We're going to let O be the set of elements. Well, let's do this in the text environment. Elements from Sn with odd order. So we'll switch this to the number of elements. The number of elements from Sn with odd order, and let's do it like this. We want to do the same thing for even, essentially. Maybe I can just copy paste this. Okay, call it E. The number of elements from Sn with even order. Okay. So, well, if you add up all the elements with even order and then the elements with odd order, that's your total elements. We have that the order of Sn is equal to, well, the number of odd elements plus the number of even elements. And further, we know that Sn is a finite subgroup with n factorial elements. So we get this equation. From part A, we showed that every element of odd order is in the alternating group. Hence, we have that the number of odd elements is less than or equal to the number of the elements from the alternating group, which is n factorial over 2. However, we're assuming that n is greater than or equal to 4. So let me scroll down. Since n is greater than or equal to 4, we have that 1, 2, 3, 4 is in Sn. Okay. And we know that the order of 1, 2, 3, 4, forgot the symbol, is equal to 2. Double transposition has order 2. So we have an element of, this is it's an even number of transpositions, so it's in An, and it has even order. Okay, so we know that An has at least all of the number of odd elements, and it has an element that is, these are the odd order ones, and it has an even order element. Okay, so this shows that the number of elements from Sn with odd order is strictly less than n factorial over 2. Okay, now we want to combine this with this equation. So we have that, let's see, if we solve for E, we get E is equal to n factorial minus O, which if we subtract something that's strictly greater than O, we're going to get something bigger. So we get n factorial minus n factorial over 2, which this is just n factorial over 2. Which is just the order of the alternating group. Okay, so what did we just show here? We showed that the number of odd elements is strictly less than the order of the alternating group, and the number of the elements of Sn with even order is strictly greater than the elements of the alternating group. Therefore, O is strictly less than E, which is what we were trying to prove. The number of elements with odd order is strictly less than the number of elements with even order if n is greater than or equal to 4. And we're done.